Hi, I'm Alex. Scientists thought they'd measured the universe 14 billion light-years, a few hundred billion galaxies, case closed. Then, a golden telescope, the James Webb, stared into perfect darkness and found 800,000 galaxies in a single patch of empty space. Structures too massive to exist, timelines that don't add up, 95% of reality hiding in plain sight. If we were this wrong about everything, what's real? Before we start, a gentle subscribe helps this channel keep growing. Now, let's begin. For decades, scientists believed they had measured the universe with reasonable precision, 14 billion light-years in every direction, a vast sphere containing a few hundred billion galaxies scattered through the darkness. The number felt enormous, yet somehow manageable. It was a cosmos humans could wrap their minds around, a reality that fit within the boundaries of comprehension. Then, on the night of December 25th, 2021, the James Webb Space Telescope turned its golden mirrors toward what appeared to be perfect emptiness, and certainty collapsed. What Webb revealed was not a universe 14 billion light-years across. It revealed an observable cosmos spanning 93 billion light-years from edge to edge, not slightly larger than expected, not double the prediction, 6.6 times larger than the universe science had confidently described for generations. The mathematics seemed impossible. The universe is roughly 13.8 billion years old. Light travels at a fixed speed. How could we observe objects more than 90 billion light-years away when light has only had 14 billion years to travel? The answer would force a complete reimagining of cosmic expansion itself. But that realization came later. In those first moments, astronomers simply stared at images that should not exist. Stars appeared where nothing was supposed to be. Fully formed galaxies materialized in regions that should have contained only hydrogen and darkness. These were not the small, dim, fragile structures predicted by every model of early cosmic evolution. They were massive. They were bright. They were already mature when the universe itself was still in its infancy. Black holes emerged at the centers of some galaxies, spinning and consuming matter at rates that violated the known limits of physics. According to conventional theory, building a supermassive black hole requires time, vast amounts of time. Material must fall inward, compress heat up, and radiate energy. That radiation pushes back against further infall, creating a natural speed limit on growth. Even under ideal conditions, assembling a billion solar mass black hole should take at least 1 billion years of continuous feeding. Webb found them when the universe was only 500 million years old. The timeline did not work. The physics did not work. Every foundational assumption about how structure forms in the universe was suddenly under interrogation. Astronomers began using a term that rarely appears in scientific literature: universe breakers. Objects whose very existence seemed to break the rules of reality itself. But the most unsettling revelation was not what Webb could see. It was what these discoveries implied about everything beyond our view. If galaxies this massive and complex already existed in the observable universe's infancy, then the true scale of cosmic evolution had been catastrophically underestimated. And if the observable universe was 6 times larger than believed, then the unobservable universe, the regions forever hidden beyond our cosmic horizon, must be incomprehensibly vast. Most of reality, it turned out, would remain permanently out of reach, not because our technology was inadequate, because the structure of space-time itself forbids access. To understand what James Webb revealed, we must first abandon a deeply human assumption that distance and time are separate things. They are not. In the universe, every measure of space is simultaneously a measure of time. This is not metaphor. It is the unavoidable consequence of light's finite speed. Light moves at 300,000 kilometers per second. It is the fastest thing that exists, fast enough to circle Earth more than 7 times in a single heartbeat. Yet even at that extraordinary velocity, distance immediately becomes delay. The farther light must travel, the older the image it carries when it finally arrives. When you look at something a mile away, you see it as it existed a few millionths of a second ago. The delay is so small it might as well not exist. Your brain treats the world as immediate and continuous. But as distance grows, the delays compound. When you look at the moon, you see it as it was 1 second in the past. When you look at the sun, you are not witnessing its current state. You are seeing light that left its surface 8 minutes ago. If the sun suddenly vanished right now, this very moment, you would not know for 8 minutes. The sky would remain bright. The warmth would continue. Only after 8 minutes would darkness arrive, delayed by the time it takes for that information to cross the void between star and planet. When you look at the center of the Milky Way, you see it as it existed 26,000 years ago. Neanderthals still walked the Earth when that light began its journey. Human civilization had not yet been imagined. The light traveled through empty space for longer than recorded history, carrying an image of a moment that ended before agriculture, before writing, before the first cities rose from river valleys. The night sky is not a snapshot of the present. It is an archive. Every point of light comes with a timestamp. Every photon is a postcard from a different era of cosmic history. The stars you see tonight are not arranged as they are now. You are looking at a three-dimensional scrapbook, each object frozen at a different moment in time, their positions scattered across thousands and millions of years. This is why astronomers do not say they are looking far away. They say they are looking back in time. Distance becomes duration. Nearby objects show the universe close to the present. Distant objects reveal progressively earlier chapters of a story already billions of years old, and this raises a question that most people never consider. If everything you see in the sky is the past, if there is no such thing as observing the present state of distant objects, then does the present even exist as a unified concept? Or is reality simply an endless collection of overlapping histories, each visible from a different vantage point, none of them synchronized? The universe is not hiding this from us. It is the fundamental nature of observation itself. Information cannot travel faster than light, therefore all information arrives late. The cosmos is not a live broadcast. It is a library of moments preserved in transit. But the universe has one more trick, one far more devious than simple delay. It does not just slow information down, it transforms it. The universe expands. This is not a controversial statement. Observations confirmed it nearly a century ago, but the implications of that expansion are far stranger than most people realize. When space expands, it does not just push galaxies apart. It stretches the light traveling between them. Light is a wave. Waves have wavelengths. When space itself stretches, those wavelengths stretch with it. Blue light becomes redder. Red light shifts into infrared. Infrared slips further into wavelengths invisible to human eyes. The process is called redshift, and it acts like a cosmic clock. The more stretched the light, the longer it has been traveling. The longer it has been traveling, the farther back in time it takes us. Ancient galaxies did not disappear. Their light simply drifted beyond the range of telescopes designed for visible wavelengths. Hubble's Space Telescope transformed our understanding of the cosmos. It captured breathtaking images of star-forming regions, distant galaxies, and the large-scale structure of the universe. But Hubble was optimized for the narrow slice of the electromagnetic spectrum that human eyes evolved to detect. As astronomers tried to look farther back in time, the universe began to fade. Not because it vanished, because its light had changed. Hubble was like trying to hear a whisper through a storm. The signal existed. The instrument simply could not detect it. James Webb Space Telescope was built to follow that missing light. Its mirror spans 6.5 meters, coated with a microscopically thin layer of gold. Gold was chosen because it reflects infrared wavelengths with extraordinary efficiency. Webb does not orbit Earth. It operates nearly 1.5 million kilometers away, at a gravitational balance point where it can remain stable, shielded from the heat and glare of both sun and planet. That distance is critical. Webb must stay cold. Extremely cold, -233 degrees Celsius. The reason is simple. And unforgiving infrared light is closely tied to heat. Anything warm emits infrared radiation. If Webb's instruments were warm, they would drown out the faint signals arriving from the edge of the universe. The telescope would blind itself with its own thermal glow. So Webb sits in the frozen darkness, waiting for photons that have crossed nearly the entire observable universe. Waiting like a hunter in a glacial forest, motionless for days at a time, listening for the faintest rustle in the undergrowth. The patience is inhuman. The precision is absolute. What Webb hears when it finally breaks that silence will keep you awake tonight, because when Webb turns toward the most distant, most ancient regions of space, it does not find tentative beginnings. It does not find a quiet universe slowly learning to form stars. It finds something far more disturbing. It hears the songs of a cosmos that was already singing when the universe had not yet learned to speak. Webb detected galaxies when the universe was only 300 million years old, less than 3% of its current age. To grasp how impossibly early this is, compress the entire history of the cosmos into a single calendar year. The Big Bang occurs at the first second of January 1st. These galaxies appear on January 2nd. Everything we know about star formation, galaxy assembly, and cosmic evolution suggests this era should be dim and chaotic. The first stars were expected to ignite, slowly, struggling against the immense pressures and temperatures of the early universe. Early galaxies were predicted to be small, fragile collections of gas, barely holding themselves together through gravity. According to every model refined over decades of research, these primitive structures would take hundreds of millions of years to mature into anything substantial. Theory painted a picture of cosmic dawn as hesitant, tentative, a universe learning to walk before it could run. Webb saw galaxies that were already sprinting. They were not dim smudges barely detectable above the noise of cosmic background radiation. They were bright, luminous enough that even if they were much farther away than calculated, Webb could still resolve them clearly. That brightness matters profoundly. Bright galaxies require vast populations of stars. Stars do more than shine. Inside their cores, nuclear fusion forges heavier elements. Carbon, oxygen, nitrogen, elements that did not exist in the universe's earliest moments. The early universe contained only hydrogen, helium, and trace amounts of lithium. Everything else had to be manufactured inside stars. And those elements are only released when stars die. When massive stars exhaust their nuclear fuel, they explode as supernovae, scattering their enriched material back into space. That debris becomes the building blocks for the next generation of stars, slightly richer in heavy elements than the generation before. This is a slow process. A star must form. It must burn through millions or billions of years of fusion. It must die. Only then can its contribution to cosmic chemistry become available. Each step imposes a minimum timescale. Compress the sequence too much and the physics stops working. When Webb detected carbon and oxygen in galaxies only 300 million years after the Big Bang, it was seeing evidence that at least one full generation of stars had already completed this cycle. Stars had formed from primordial gas. They had lived, they had died. Their remains had already enriched their surroundings enough to leave spectroscopic fingerprints visible across 13 billion years of cosmic time. The universe was not just forming its first stars at cosmic dawn. It had already cycled through stellar birth and death multiple times. The cosmic clock was not running slow. It was being pushed backward, forced into a timeline that should not physically accommodate what observations clearly revealed. If the universe is a construction site, then, according to theory, cosmic dawn should show us the foundations being poured, raw materials being delivered, plans being drawn up. Instead, Webb found skyscrapers, finished buildings with running water, electricity, and fully furnished apartments. Not impossible in principle, but impossible given the amount of time available between the Big Bang and the moment that light was emitted. Gravity is powerful, but it is not instantaneous. Gas clouds must lose energy before they can collapse into stars. Dark matter halos must accumulate enough mass to trap ordinary matter in their gravitational wells. Stars take millions of years to form, and many more millions to complete their life cycles. Each stage depends on the one before it. You cannot construct a skyscraper before producing steel. You cannot forge steel before mining iron. You cannot mine iron before planets form from stellar debris. Yet here were galaxies displaying chemical maturity that required multiple generations of stellar processing existing when the universe had barely passed its 300th million birthday. The question astronomers faced was unavoidable and deeply unsettling. If there was not enough time for these objects to exist, then how were they there? The cosmic clock was not just running backward, it was being destroyed. Some of the galaxies Webb detected were so bright, so massive, and so chemically mature that scientists briefly struggled to explain them within any existing framework of cosmology. These objects exceeded theoretical predictions by factors of 5, sometimes 10. Not small discrepancies that could be explained by measurement error or observational bias. fundamental violations of what was thought possible. The total amount of light these galaxies emitted suggested they contained hundreds of millions, even billions of stellar masses worth of material. Building that much structure requires time. Dark matter must clump, gas must cool and collapse, stars must form in vast numbers. According to standard models, assembling galaxies of this scale should take at least 500 million to 1 billion years. The universe simply had not been around long enough. Researchers began referring to them half-jokingly and half-seriously as universe breakers, objects whose existence seemed to shatter the rules. The term captured the shock rippling through the astronomical community. These were not anomalies that could be quietly filed away as outliers. They appeared again and again in different surveys in different regions of sky, using different instruments. The pattern was consistent. The early universe was not scarcely populated with dim proto-galaxies. It was crowded with luminous, massive systems already undergoing intense star formation. Even more troubling were the supermassive black holes. Webb identified black holes weighing millions, sometimes billions of times the mass of our Sun, already spinning at the centers of galaxies when the universe was only 500 million years old. According to conventional astrophysics, this should be flatly impossible. Black holes grow by consuming surrounding matter, but that growth has a natural speed limit. As material spirals inward toward a black hole, it heats up through friction and compression. That heat produces radiation. Intense radiation. The radiation pushes back against further infall, creating an effect called the Eddington limit. Even a black hole feeding at maximum efficiency, consuming matter as fast as physics allows, should take at least 1 to 2 billion years of continuous feeding to reach 1 billion solar masses. The universe, at 500 million years old, had not provided that much time, not even close. It would be like discovering a 6-month-old infant casually lifting 200 kilograms above their head. Not merely surprising, physically incoherent given everything we understand about growth, development, and the passage of time. 3 possibilities emerged, none of them comfortable. Either the measurements were wrong, or the assumptions about how black holes grow were wrong, or something fundamental about the early universe's behavior was misunderstood. Multiple teams rechecked the data. They reanalyzed the spectra. They questioned whether gravitational lensing or other effects might be inflating the apparent brightness and mass of these objects. The numbers held, again and again they held. This forced cosmologists into unfamiliar territory. Perhaps black holes formed through mechanisms no one had seriously considered. Perhaps massive gas clouds collapsed directly into large black holes without passing through a stellar phase first. Perhaps the first stars were thousands of times more massive than modern stars collapsing into unusually large seed black holes. Perhaps mergers between black holes were far more common in the dense early universe than current models assumed. Each explanation helped. None fully resolved the tension. The early universe remained stubbornly brighter, more massive, and more organized than theory predicted it should be. If the physics was wrong from the beginning, then what else might be wrong? How many other assumptions built over decades of careful observation and modeling were quietly collapsing under the weight of Webb's revelations? The discoveries ahead will completely shatter your conception of cosmic scale, because Webb did something deceptively simple. It counted, and the result left NASA in stunned silence. Throughout the 20th century, astronomers believed they had achieved a reasonable census of the universe. The Hubble Space Telescope performed its deepest observations by pointing at a patch of sky no larger than a grain of sand held at arm's length. The region appeared utterly black to the naked eye, empty, devoid of anything interesting. Hubble stared at that darkness for days. When the exposure was complete, nearly 10,000 galaxies filled the frame. The image was shocking. From that single observation, astronomers extrapolated across the entire sky and arrived at an estimate that stood for 3 decades. A few 100 billion galaxies exist in the observable universe. The number felt simultaneously enormous and finite, incomprehensible yet somehow bounded. It became the standard figure cited in textbooks, documentaries, and scientific papers. Humanity had counted the cosmos. Then James Webb looked at the exact same patch of sky. 800,000 galaxies. Not 10,000. 800,000 distinct objects, each one a galaxy containing millions to trillions of stars. If you printed the famous Hubble Deep Field on a standard sheet of paper, you would need to print Webb's equivalent image at over 4 meters tall to capture the same level of detail. A wall-sized mural of cosmic history, and every single point of light represents not a star but an entire galaxy. Every one of those galaxies hosts billions of stars. Many of those stars have planetary systems. Some of those planets harbor complex chemistry, organic molecules, perhaps even the conditions necessary for life. The universe is not sparsely populated, with isolated islands of matter drifting through emptiness. It is densely packed, layered with structure at every conceivable scale. What makes this discovery even more profound is what Webb revealed in the spaces between galaxies. The regions Hubble saw as black gaps, true voids separating one galaxy from another, turned out to be anything but empty. Webb detected faint infrared glows, dozens, sometimes hundreds of dim galaxies hiding in what was assumed to be pure vacuum. The gaps were crowded, the voids were full. Darkness was an illusion created by the limitations of visible light astronomy. If emptiness is actually teeming with hidden structure, then what else have we misunderstood about the nature of space itself? How much of what we call vacuum is simply matter? We lack the tools to detect. The universe does not reveal itself easily. It hides behind wavelengths our eyes cannot see, behind distances our instruments struggle to measure, behind timescales that dwarf human history. It would be like discovering that the apartment you believed was empty actually contains 80 people standing perfectly still in the darkness, invisible, until someone turns on the right kind of light. The space did not change. Your perception of it did, and once you see them, you cannot unsee them. The emptiness you trusted was never real. The universe is not empty. And the way these galaxies arrange themselves is even more unnerving than their sheer number. Galaxies do not scatter randomly through space like sand grains thrown across a floor. They organize, they cluster, they align along vast structures stretching 100 to 200 million light-years across. These structures are called filaments, and they form the largest coherent architecture in the universe, a cosmic web. At the intersections of these filaments sit massive galaxy clusters, dense regions where hundreds or thousands of galaxies crowd together under mutual gravitational influence. Between the filaments stretch the true voids, immense regions of near-absolute darkness spanning 100 million light-years or more. If you could place yourself at the center of one of these voids and look in any direction, you would see nothing but blackness for tens of millions of light-years before encountering the nearest galaxy. The universe is simultaneously crowded and empty, rich and barren, structured and desolate, depending entirely on where you look. Webb detected one particularly striking example of this organization. Astronomers call it the cosmic vine. It is a chain of at least 20 closely packed galaxies, stretching more than 13 million light-years across space. These galaxies existed when the universe was still young, yet the structure rivals formations found in much older cosmic epochs. What makes the cosmic vine especially intriguing is not just its scale but its state. Several of the largest galaxies within the structure have already stopped forming stars. They are quiescent, dead in a sense. They exhausted or lost the gas necessary to create new stars, and now they simply exist, their stellar populations aging slowly while no new generations ignite. This is profoundly unusual so early in cosmic history. Most galaxies at this epoch are still actively forming stars, consuming gas and dust at furious rates. The fact that some galaxies in the cosmic vine have already shut down suggests that environment matters. Galaxies in dense, crowded regions evolve differently than isolated ones. Interactions, mergers, and the harsh radiation environment of clustered space can accelerate a galaxy's life cycle, forcing it to mature rapidly and burn out early. It is the cosmic equivalent of cities versus rural towns. Dense urban environments change their inhabitants faster, imposing pressures and opportunities that do not exist in isolation. The cosmic vine shows that galaxies like civilizations are shaped by their neighbors. Using Webb's data, astronomers compiled the deepest and most comprehensive catalogue of galaxy groups ever assembled. They identified more than 1,600 groups and protoclusters spanning from roughly 12 billion years ago to just a few billion years ago. For the first time, scientists could watch cosmic structure evolve continuously across vast stretches of time. Early groups appear chaotic, Galaxies are irregular, asymmetric, actively forming stars at intense rates. Later groups show more order. Galaxies become smoother, more elliptical. Star formation slows. Gravity begins to dominate over turbulence and gas inflow. The universe learns to organize itself. If the universe has a skeleton, then who built it? The answer is uncomfortable. No one built it. It assembled itself. Gravity, acting on tiny fluctuations, imprinted during the universe's earliest moments, carved space into filaments and voids over billions of years. Structure emerged not from design but from mathematics, from physics operating without intention or purpose. This is why the story cannot stop halfway, because understanding the cosmic web requires confronting a number that breaks the human brain. The universe is 13.8 billion years old. Light has had 13.8 billion years to travel since the Big Bang. Logic suggests that the farthest objects we can observe should be roughly 13.8 billion light-years away. The observable universe should have a radius of 13.8 billion light-years, making its diameter about 27.6 billion light-years. That intuition is wrong, catastrophically wrong. The observable universe has a radius of approximately 46.5 billion light-years. Its diameter spans roughly 93 billion light-years. This is not speculation. It is a measured result, supported by observations of cosmic expansion and the behavior of ancient light. The number sounds impossible. It feels like a violation of the cosmic speed limit. Nothing can travel faster than light through space. That rule remains absolute. No galaxy is racing outward at impossible velocities. No signal is breaking the laws of physics. And yet the universe has found a way to grow far larger than its age should allow. It does this by stretching space itself. When distant galaxies move away from us, it is tempting to imagine them flying through space like fragments from an explosion. That picture is deeply misleading. On cosmological scales, galaxies are not moving through space at all. They are being carried apart as the space between them expands. The distinction is subtle but essential. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, every dot moves farther away from every other dot. None of the dots are sliding across the surface under their own power. The surface itself is stretching and the dots go along for the ride. The universe behaves in much the same way. When a distant galaxy emitted the light we detect today, it was far closer to us than it is now. Over billions of years, while that light was traveling toward Earth, the space between us and the galaxy expanded continuously. By the time the light finally arrived, the galaxy had been carried tens of billions of light-years farther away. Light from a galaxy 13.5 billion years old has indeed been traveling for 13.5 billion years. But during that entire journey, space was expanding. The galaxy that emitted the light is now more than 46 billion light-years away, even though the light itself only traveled for less than 14 billion years. It is like running on an airport moving walkway that is traveling in the opposite direction faster than you can run. You move forward relative to the walkway itself, but the walkway carries you backward faster than your legs can compensate. By the time you stop running, you are farther from your starting point than the distance you actually ran. If the starting point keeps receding faster than you can approach it, are you truly moving forward, or are you caught in a system where progress and retreat happen simultaneously, neither one fully cancelling the other? And 93 billion light-years is only what we can see. The observable universe ends at a boundary called the cosmic horizon. It sits roughly 46.5 billion light-years away in every direction, forming a spherical shell around Earth. This is not a physical edge. There is no wall, no place where space suddenly stops. The horizon is simply the limit of what light has had time to reach us since the Big Bang. Beyond that horizon, galaxies still exist. Stars still ignite and die. Black holes still merge. Entire cosmic histories unfold in regions forever hidden from view. Their light has not reached us yet, and for many of them, it never will. The reason is brutal in its simplicity. Space expands faster than light can cross it. Light from galaxies beyond the cosmic horizon is traveling toward us right now. Those photons are moving at maximum speed, covering 300,000 kilometers every second. But the space they must traverse is growing faster than they can cross it. The finish line recedes more quickly than the runners can approach. Light runs at full speed yet makes no progress. Eventually, as expansion accelerates, those photons will begin losing ground. The gap will widen. The light will never arrive. What makes this even more disturbing is that the horizon is not static. It moves. As cosmic expansion accelerates, driven by dark energy galaxies that are currently visible will eventually slip beyond reach. The observable universe is shrinking in terms of what future observers will be able to see. In 100 to 150 billion years, every galaxy outside our local gravitationally bound group will cross the cosmic horizon. Future astronomers will look up and see only a small cluster of nearby galaxies surrounded by infinite darkness. The cosmic microwave background will have redshifted into undetectable wavelengths. The evidence for the Big Bang will be gone. The proof of cosmic expansion will vanish. Those future observers will have no way of knowing that anything else ever existed. They will believe they inhabit a small static universe containing only a handful of galaxies in an otherwise empty cosmos. They will never discover the truth because the truth will have been erased by the structure of space-time itself. Are we in the same position? Are there phenomena, structures, entire categories of cosmic reality that have already slipped beyond our horizon, leaving no evidence of their existence? Have we lost information about the universe's true nature simply because we arrived too late to witness it? It is like logging into a streaming service only to discover that 99.9% of the content has been deleted overnight. No warning, no record of what was removed, just an empty library and the vague sense that something is missing. This is why Webb matters. It is capturing images before they vanish forever. It is documenting a universe that is actively disappearing. Every distant galaxy Webb observes is one step closer to crossing the horizon, one snapshot closer to becoming permanently inaccessible to future science. But the force pushing galaxies across that boundary is the most terrifying entity in the cosmos. In the 1990s, astronomers set out to measure how fast the universe's expansion was slowing down. The assumption seemed safe. The Big Bang had flung everything outward. Gravity had been working ever since to pull it all back together. Expansion should be decelerating. The only question was how much. They measured the velocities of distant galaxies using Type Ia supernovae, stellar explosions that shine with remarkably consistent brightness. By comparing how bright these supernovae appeared to how bright they should be, scientists could calculate precise distances, combine those distances with recession velocities, and the expansion history of the universe reveals itself. The results were shocking. The universe was not slowing down, it was speeding up. Distant galaxies were farther away than they should have been if expansion were gradually easing under gravity's pull. Something was pushing space apart. Not just preserving the expansion inherited from the Big Bang, but actively accelerating it. The farther back astronomers looked, the clearer the pattern became. For billions of years, cosmic expansion had been gaining speed. To account for this behavior, cosmology was forced to introduce a new ingredient: dark energy. Dark energy is not something we can see, touch, or directly detect. It does not emit light. It does not absorb radiation. It does not clump into stars, galaxies, or clouds. Its existence is inferred entirely from its effect on the universe's expansion, and that effect is overwhelming. Current measurements indicate that dark energy makes up roughly 68% of everything that exists. 68%. More than 2/3 of reality is composed of something completely invisible and fundamentally mysterious. Ordinary matter, everything from galaxies and stars to planets and people, accounts for less than 5%. Dark matter makes up most of the remainder. The universe we can see, the universe that feels solid and familiar, is a minor component of existence. A thin film of visibility stretched across an invisible foundation. What makes dark energy especially unsettling is how it behaves as the universe grows. Normal matter becomes diluted as space expands. Double the volume of space and the density of matter drops by half. Spread the same amount of material across a larger area and it becomes correspondingly thinner. Radiation dilutes even faster, losing energy as its wavelengths stretch. Dark energy does not follow these rules. Its density remains constant even as the universe expands. As space grows larger, the total amount of dark energy increases. More space means more dark energy. More dark energy drives faster expansion. Faster expansion creates more space. The cycle reinforces itself. This creates a runaway feedback loop. Early in cosmic history, matter dominated. Gravity sculpted galaxies, stars, and the cosmic web. But as the universe expanded and matter spread thinner, dark energy quietly accumulated. About 5 billion years ago, dark energy overtook matter and seized control. Since then, it has been driving cosmic expansion faster and faster, pushing galaxies apart with ever-increasing force. If 68% of reality is invisible, can you truly claim to see the world, or are you looking at shadows cast by forces you cannot perceive, mistaking the surface for the substance? It is like discovering that 68% of your body is made of ghost matter. You feel solid, you appear complete. But most of what constitutes you exists in a form you cannot touch, measure, or understand. You are less real than you believed. And dark energy is causing the most severe crisis in physics. There are two ways to measure how fast the universe is expanding today. Both methods are precise. Both have been repeated many times by independent teams. Both produce confident, well-supported results, and they do not agree. The first method looks deep into the past by studying the cosmic microwave background, the faint radiation released when the universe was only about 3,800,000 years old. From the subtle patterns imprinted in that ancient light, scientists can infer the expansion rate. The answer: approximately 67 kilometers per second per megaparsec. The second method looks nearby. Astronomers measure distances to galaxies using Cepheid variable stars and Type Ia supernovae, then compare those distances to how fast the galaxies are receding. This approach consistently produces a higher value, around 73 kilometers per second per megaparsec. 9% higher. Both measurements are accurate. Both have been scrutinized for systematic errors. Both hold up under repeated testing. They simply do not match. This discrepancy is known as the Hubble tension, and it represents one of the deepest fractures in modern cosmology. James Webb was expected to resolve the issue by providing cleaner, more accurate distance measurements. Instead, Webb confirmed the higher expansion rate measured in the nearby universe. The tension did not disappear. It sharpened. 3 possibilities remain, and none of them are comfortable. Either the measurements are wrong in ways no one has identified, or the assumptions underlying our cosmological models are wrong, or the physics itself is wrong. The consequences extend far beyond a single number. The expansion rate determines the universe's age, its size, its ultimate fate. If we are measuring it incorrectly, then many conclusions drawn from decades of research may require fundamental revision. The cosmic timeline could be shorter or longer than believed. The observable universe could be larger or smaller. The amount of dark energy could be increasing, decreasing, or behaving in ways current models cannot capture. One extreme scenario cannot yet be ruled out. If dark energy grows stronger over time, instead of remaining constant, expansion could eventually overwhelm gravity even on small scales. Galaxy clusters would be pulled apart. Galaxies themselves would dissolve. Star systems, planets, molecules, and eventually atoms could be torn to pieces in a hypothetical future known as the Big Rip. Current data does not favor this outcome, but uncertainties remain large enough that the possibility cannot be dismissed. Small changes in how dark energy behaves could have catastrophic long-term consequences. If two truths are both correct but contradict each other, has reality itself fractured? Or does the contradiction reveal that reality operates by rules we have not yet discovered? It is like visiting 2 doctors for the same examination. One tells you confidently that you will live 50 more years. The other tells you with equal confidence that you have 30 years remaining. Both are experts. Both used rigorous methods. Both are certain. How do you reconcile information that should align but does not? This is why you must watch until the final moment, because the answer is stranger than the question. And dark energy is only half the story. The other half is even more ghostly. 85% of all matter in the universe is invisible, not hidden behind dust, not too faint to detect, fundamentally irreducibly invisible. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation in any way we can directly observe. And yet it outweighs everything we can see by more than 5 to 1. The first hints of its existence emerged nearly a century ago when astronomers noticed something wrong with galaxy rotation. Stars in the outer regions of spiral galaxies were orbiting far too fast. According to the gravity generated by visible matter alone, those stars should have been flung into intergalactic space. Instead, they remained bound, moving as if each galaxy were embedded in a massive invisible halo. Galaxy clusters showed the same problem on larger scales. Individual galaxies within clusters moved too quickly to be held together by stars and gas alone. Gravitational lensing revealed that light from background galaxies was being bent by mass concentrations far stronger than visible matter could produce. Again and again, the evidence pointed to the same conclusion. Most of the universe's matter does not shine. This invisible substance is called dark matter, and it forms the scaffolding of cosmic structure. Shortly after the Big Bang, when the universe was still hot and dense, dark matter began clumping first. Unlike ordinary matter, it does not collide with itself. It does not lose energy by emitting radiation. It passes through space almost frictionlessly, responding only to gravity. This allowed dark matter to begin gathering extraordinarily early in cosmic history. While ordinary matter remained hot and resisted, collapsed dark matter quietly accumulated into growing concentrations. It formed massive halos long before the first stars ignited. These halos became gravitational wells. As the universe cooled, ordinary matter fell into those wells, compressed, and eventually ignited nuclear fusion. Stars formed, galaxies assembled, not randomly but precisely where dark matter had already gathered. The visible universe traces an invisible blueprint laid down billions of years earlier. On the largest scales, this process produced the cosmic web. Dark matter does not distribute itself evenly. It forms filaments stretching hundreds of millions of light years across space. These filaments intersect at dense nodes where galaxy clusters form. Between them lie vast voids regions so empty they contain almost no matter at all. Recently, astronomers achieved something remarkable. They detected dark matter directly along the filaments themselves. Using gravitational lensing, scientists measured how light from distant background galaxies was subtly distorted as it passed through regions where filaments were predicted to exist. The distortions were faint but consistent. They revealed mass where no visible matter could account for it. Dark matter was not just concentrated in clusters. It stretched across space, threading the universe together. The cosmic web transformed from theoretical construct into observed reality. Ordinary matter flows along these dark matter highways like traffic on cosmic roads. Gas streams toward galaxy clusters, following paths carved by invisible structure. Even our own galaxy participates. The Milky Way resides on a dark matter filament drifting through space, along pathways defined by forces we cannot see. If 95% of the universe is invisible, is the reality you perceive actually real? Or are you living inside a transparent house surrounded by walls, floors, and ceilings, and you cannot touch? Mistaking the furniture for the architecture. It is like spending your entire life in a building, only to discover one day that the walls, floor, and ceiling are made of perfectly transparent material. The structure was always there, holding everything together, defining the space you inhabited. You simply could not see it, and once you realize the truth, every room you ever walked through feels different. The emptiness was never empty. The solidity was never solid. Everything leads to a final truth, and it will change how you look at the night sky tonight.